Let me record now. It is just a matter of expressing vectors. Okay, vectors with respect to the x, y, and z components of that reference frame that we are trying to reference our position or orientation. Okay, so that's the basic idea. So now let me share screen again. I mean, that is just, you know, it's not that very big of an issue. It's easy to understand. Okay, let me. Okay, there. So let me recap. In terms of position, we are dealing with a vector that has, excuse me, we don't have a control over the length of the vector, yeah, because we don't know whether this vector can be very far, 100 kilometers, 500. We don't have that control, because exactly that is what we are looking for. We want to know the distance. Okay, we want to know the position of this point, the end of that vector, with respect to the base of it. Yeah, so now this one, that's why we want to express this vector with respect to the x, y, and z component of this frame that we are trying to express it. Okay, now, but in terms of orientation, we don't deal with that magnitude of a vector. We only deal with vectors that are unit vectors. The magnitude is 1. Okay, that's the basic difference. Yeah, so now if this was frame 2, the x and y and z component of frame 2, okay, then we want to express each of these unitary vector. This is a unit vector, this is a unit vector, and that's a unit vector. Express them with respect to the x, y, and z of frame 1. Okay, so of course here is frame 2, x2. We want to express it in terms of frame 1. Okay, so y2 and z2. Okay, so we express each of those vectors. This is your x2 with respect to frame 1. This is your x3. I mean, sorry. That's your y2 with respect to frame 1. And this is your z2 with respect to frame 1. Again, those vectors are unitary vectors. Okay. So what happens then if you want to express frame 2 with respect to frame 2 to itself? What happens? Okay, let's check. Okay, let's do that. So I want to express frame 2 with respect to frame 2. So for example, this is your x, this is your y, this is your y, and this is your z. Okay, so we know that if you express, we know that if you express x2, y2, and z2 with respect to itself, this is what? 1, 0, 0, right? And this is 0, 1, 0. And this is 0, 0, 1. Okay? So that means that rotation of 2 with respect to itself, to 2, is equal to what? That's 1, 0, 0, 1, 0, 0, then 0, 1, 0, and 0, 0, 1. There. And what is that? is an identity matrix. Okay? It's an identity. It's just identical. The vector, the frame is identical to itself. There's no rotation. Okay? So the same thing, for example, if the orientation of frame 2 is the same orientation as frame 1, so maybe this is the same as, okay, let me change the color. This is coincident to Z1, okay, exactly the same. This is also coincident to X1, exactly the same vector, and coincident to Y1. Okay. If that is the case, then what happens here? Well, it says that, again, it will be identity. Yeah. That means that the orientation of frame 2 with respect to frame 1, frame 2 with respect to frame 1 is identical. They are not rotating. They are identical to each other. There's no rotation. Okay. Okay. Now let's look at some basic rotations. So, for example, X1 is rotated 90 degrees. Okay. So let's check. For example, we say, what about, sir? If we say rotated, or let's just say there's a rotation of, okay, let's just rotate Z. Okay. The rotation of 2 with respect to frame 1. Okay. Okay. About the Z axis. Okay. About, let's say, about that axis is equal to the rotation about this one Z2 axis is, let's say, for example, let's just say 180 degrees. So it's okay. So if that is the case, that means that our frame 1, for example, this is frame 1, X1, Y1, Z1. Okay. If that is the case, now we rotate to reach to frame 2. It's rotated by 180 degrees around about here. So 180 degrees. Okay. So that means here your X1, your X from here rotated 180 degrees. So this is your X2. Your Z2 remains the same. And your Y2 is there. Okay, so you rotate 180 degrees from here, rotate 180 degrees so that your X2 is there. Okay, your X2 is in this direction, and then your Y2 is in that direction. That's rotated by 180 degrees. Okay, so now what is your rotation matrix? So in that case, now we say, let's change the 1R2 will be equal to, well, your Z-axis remains the same. Okay, your Z2 and Z1 remains the same, so that is just 0, 0, 0, 1. What about your X2 with respect to X1? So remember, this is X2 with respect to 1. What is that? Okay. So is your Z still 0? Right. Your Z still 0. What is the Y component? Still 0. What is your Z component now? Your Z component, this is 1. Remember, that's 1. And now this one is also 1, but then it's negative. Okay, so negative 1. There. What is your Now, what is your 1, y2? So your 1, y2, the z component is still 0, so that's 0. What about the x component? Are still 0? Yes, there's no component with respect to the x, that's still 0. What about your y? Your y changes. So your y now, in terms of a 1, it becomes a -1. -1. There. That's it. So if you want 180 degrees rotation with respect to the z-axis, there you see, the z-axis doesn't change as a 1. Only the x component and the y component becomes a -1. Okay, well, that's how the relationship of rotation is. Yeah, so now you have an understanding now of how are those rotations related to, I mean, rotation of one reference frame 2 with respect to reference frame 1. Okay, so we can fully express the relationship of those rotations by expressing the components of each of the axes, x, y, and z axis of frame 2 with respect to frame 1. Okay, that is the rotation. Okay, that's how we express rotations. Okay. Now let's continue. So, but reference frames are very complicated. Yeah, you don't want to go there first. Okay, what I want you to understand is because we're going, the main problem here is we want to control the I'm just checking your faces if you are there. We are going to control the hand movement of the robot with respect to the base frame. Okay, in this class, well, if you have more time, also the posture of the arm. Posture meaning how is the arm, whether it's up elbow or down elbow, or what kind of position, of what kind of posture of the arm, so that we can achieve the same hand position. Okay, so before we do that, before we use reference frames, let's just compute mathematically what happens to the hand position of the robot when each of the joints are moving. Okay, so in this case, we have a planar robot. Yeah, let's consider a planar robot. Okay, planar robot, that means it lives in a plane. It moves within this plane. Okay, it doesn't move outside of the plane. So now your rotation, you rotate about this axis, okay, which is your Z0 axis, going out of the paper, and then you have Z1 axis going out of the paper also. Okay, so each of those joints are moving about the Z axis. They live in a plane, okay, of the XY plane. So now, if this is the case, we don't need to consider yet, although we can still consider the use of rotation matrices and position vectors and transforming them. There's no problem. But I want you to see that here we can solve it analytically by just using the normal way of doing things, just like what we know about, in terms of taking the components of the X and the Y axis like that, without considering those rotation matrices. Okay, how? Well, it's easy. Let's check. Now, what is this component? Okay, to know the position of this hand with respect to the base, we just need to compute this distance, right? Okay, that's the hand, or that's the X. And also we need to compute that distance, your Y. Yeah, but that Y is composed of this component, of this distance, plus another, that distance. And the same thing as your X, this distance, plus this distance. Well, it's easy. Geometrically, we can see that. So this distance is this, L1 cosine of theta 1, where theta 1 is this, theta 1. Okay, that's L1 cosine of theta 1. Yeah, so check. Okay, well, let me change the color. Okay, so this is your theta 1, and that is your L1. So L1 cosine of theta 1, that's correct. That is your X. This is your distance. Okay, now what is this distance? Okay, because theta 2 is taken based on frame 1. Okay, well, your frame 1 is this frame that moves together with the joint. So now this was theta 1. Okay, this was theta 1, the same as that theta 1. So now you add these two components, theta 1 plus theta 2. That means L2 cosine of theta 1 plus theta 2. This part here. L2 times cosine of theta 1 plus theta 2, because that's the total angle. So now that is that part. Okay, so you express X. Yeah, it's easy. So now we express Y. So again, L1 instead of this one, L1 cosine is L1 sine. So this part is that. Okay, plus again L1, the total angle, sine of the total angle, L2 times the sine of total angle. That's it, finish. That is the X position of the hand and the Y position of the hand. Understand? Okay. Okay, so that's clear, I guess. So now let's continue. So let's have an octave. This is where your lab exercise number 1. You should be ready to answer this lab exercise number 1, only forward kinematics. Okay, let's run the octave. Where's my octave? Okay, so let's run the octave example of robot 1. Okay, so let's check this. Let's understand this diagram first. Okay, let's maximize it. So now let's understand this. So what is this? This is the robot. This is the link 1. This is only one link. Yeah, this is the base of the robot. Okay, and this is the hand of the robot. Okay, then this robot moves from horizontal going up to, I think, 45 degrees. Or is it, oh no, maybe 60 degrees. Okay, so now what happens here is that I am plotting this is the hand, yeah? So that hand has two components. HX, okay, that is the H, the hand along the y-axis, and the hand along the, the hand along the y-axis, and the hand along the component of the hand along the x-axis, component of the hand along the y-axis. So that means that here, okay, when you're horizontal, H is equal to HX, yeah? Totally. And then your HY is 0, yeah? Your HY is 0. Okay? So anyway, as you go here, you always have HX and HY component, correct? As you go here, you have another HX and HY component. You go here again, so each of these are different values of HX and HY, okay? As your angle changes, I think the angle here is changed every 1 degree or 2 degrees, I don't know. The angle goes from 0 to, it's not 60, it's 50 something, 58. Oh, I don't know why it's not 60. Anyway, so the elbow angle goes from 0 to, let's just say 58, yeah? So at increments of probably let's just say 1 degree. Okay, so every degree the robot moves there. Oh no, not maybe 5 degrees. Yeah, maybe 5 degrees. So every time the robot is plotting, I mean taking the value every maybe 5 degree or so. Let's just say 5 degrees. So every 5 degrees you go up, okay, and take those values. And then now you plot the values of that hand. So because every time here you have an L, well, you have an X is equal to L times cosine of theta. And then your Y is equal to L times sine of theta, where your theta is that theta angle. So that's why this X is actually your HX and Y is your HY. Okay, so what we are saying here is that whenever the angles change in the joint, your hand move accordingly like this. Your hand with respect to the Y-axis moves like that. Your hand with respect to the X-axis moves like this. Okay, from a bigger number to a smaller number. Is that correct? Look at the HX here. It starts from around 0.45 to around 0.3. Yeah, to around or somewhere there, 0.3. Okay, is that correct? Well, let's look at here. Okay, so the length is about here is about 0.45. And it goes down. You see, it goes down as the angle changes. It goes down to some small value, around 0.3. Okay, that's how the hand moves. Okay, now with respect to the Y-axis, well, we say you see your hand of the X from a bigger number to a smaller number. Yeah, but the Y-axis is starting from 0 because these are the components. 0 up to a certain number here, a bigger number. Yeah, it keeps on increasing. So the HY then starts from 0 and then it increases until this value. Okay, so if you track the position of the hand as the angle changes, this is the position of the hand about Y, about X, and this is the position of the hand about Y. Okay, now let's see that in the. Let's do it by doing incrementing it one by one. Okay, let me run. Okay. Okay, so this is your robot initially. Okay. Okay, then let me. Okay, it goes here, there. So this is your robot initially like that, flat, and then it goes up, and then your hand, the position of the hand do like this, and then the angles, of course, every 10 degrees. So 10 degrees, maybe 5, because there are 2 points here already. So now let's do it incrementally. So move. Okay, it doesn't go here. There, move. Continue moving until there it reaches. Okay, let me do it one more time. So in your exercise, you're going to do this. Move. Okay, it doesn't, because this one is already flat. We cannot see. Let's do another one. Okay. Then move. Okay. So we move. Okay. Move the angle. So move the hand, move the angles, go up. The angles is the independent variable. Yeah. The angle moves, and then the dependent variable, the hand will have a position based on the angle that is moving. Yeah. So move. There, the hand move. This X goes down and the Y goes up. X goes down, Y goes up until it reaches the final destination. Okay, as you move here, your angle increases, and your hand HX decreases, and your HY increases. Okay, I hope that is clear. Now, that is for one link. Now we want to do two links. Okay. Now you have two links. I'm just showing you that the hand movement with respect to the joints. Okay. There. So now the joint, okay, I'll just keep on pressing this. Okay, so joint one here, in this case, this is joint one, and this is joint two. It's not labeled. So this is joint one, 0, and joint one remains at 0, while joint two is incremented every 10 degrees, I think. So 10 degrees, so it will keep on moving like that. And this, because this is not, I should position this so that it will be square and it will look. You see? Okay. That's the hand. That's how the hand moves as we increment the joint angles. Okay. Okay, let's do it one more time. Okay, I want to make it square so that we can see it square, not there. There. Okay. So the frame joint 0 here, I mean joint 1 remains at 0. So joint 1 remains at 0, and we increment by 10 degrees. So only joint 2 increases. Yeah. So the hand sweeps around here because it increases the joint 2 angle. Okay, it sweeps. Now joint 1 is incremented at, I think, 10 degrees. So joint 1 increase at 10 degrees. So it goes up from 0 here, it goes up here. Yeah, so from 0 it goes up here, and then now joint 2 is 0. So now this new robot configuration is where this joint 2 will sweep, because we're going to increment one by one. We're going to increment by 10 degrees again. Yeah, so joint 1 or the link 1 is here steady because it's remaining at 10 degrees, the joint 1 angle, and then joint 2 now sweeps. Joint 2 sweeps from 0 to again around 160. There, it sweeps, yeah, like a fan. Okay, now the same thing. Now joint 3, I mean joint 1 is increased at 30 degrees. So then joint 2 sweeps, okay, and then joint 1 again increased by now I think around 40 degrees, and then joint 2 will sweep, yeah, like a fan. Joint 2 like that. Joint. So I keep on increasing joint 1, and then keep it constant, and joint 2 is sweeping. Okay, so joint 1 like that, and then joint 2 sweeps. Okay, so as you can see, when you keep on incrementing the joints, well, the movement of the hand is like that. Yeah, it's almost like random. We don't have any control. Okay, so what is the purpose here then? Well, the purpose is just to show you what is the corresponding movement of the hand with increments in the joint angles. Okay, but this is not the way we control things. The way we that's why we don't control in terms of the joints. We control the movement by the hand movement. Okay, so now if you want, this is what is called forward kinematics. Forward kinematics meaning to say that we compute, okay, we compute your x, hx, and hy, we compute the hand movement with respect to the joint angles. In this case, theta 1 and theta 2. Okay, this is what we call forward kinematics. The independent variable are the joint angles and the dependent variables are the hand position. Okay. Now, what is inverse kinematics? Well, inverse kinematics is when we take the inverse of that function. It will be theta 1. We solve for theta 1 and theta 2. If there's forward, that means there must be inverse or backward. So the inverse of that f function, now given the hand position, excuse me. Okay, this is what we call the inverse kinematics. What does it mean? It means that we know where the hand will move. Okay, we want to put the hand here. Okay, this is where we want the hand to be, and then we solve what will be the joint angles that's necessary in order for the hand to be there. So this is the one that is more meaningful. This is the more meaningful motion in terms of robot control. And we do a lot of this inverse kinematics so that we will know how will the joints move in order to achieve the hand movement. Okay, but for now, I'm just showing you the forward kinematics so that you will understand, because this is a necessary computation in order to go here to the inverse kinematics. Okay, so for you to understand what is the relationship between the hand position, which is here, with respect to the joint position or to the joint movement. Okay, so now let's continue. Okay, we're done with robot 1 and robot 2, and this is the drawing, and this is also the joint space and the hand space in terms of position. Now, so we are familiar now with how the hand moves when the joint moves. That's forward kinematics. Now, we say that there is a robot Jacobian, and this robot Jacobian expresses a linear relationship between the increment of the joint movement against the increment in the hand movement. Okay, and how is this being expressed? We say that there is a linear relationship. Okay, the increment movement of the hand, okay, is equal to the Jacobian times the incremental movement of the joints. Okay, and it's linear. Okay, so that's the basic definition of a Jacobian matrix. So if we take, therefore, okay,